I'm Keutzer, and today I'll be talking about efficient deep learning. And I just want to say that this work that I'll be presenting today is the result of the efforts of many people. So you notice I said deep learning and not more broadly artificial intelligence and machine learning, and I will describe those in more detail later. The definition of artificial intelligence is always evolving, and machine learning, I think we can say generally, is a set of data-driven algorithms rooted in statistics. And deep learning is actually, as I show here, a relatively small subset of machine learning approaches. So when we have an ordinary algorithm, we define its behavior entirely deterministically, and then express that in an imperative programming language such as C, C++, or Java. When we have a machine learning algorithm, in particular supervised machine learning, we really just define a template of behavior. And then the precise behavior of the algorithm becomes defined based on data sets which are used for training. Now, we worked for a number of years, my research group, on applying machine learning. In particular, we were focused on accelerated machine learning algorithms, and we did that across a variety of problems in computer vision, as well as core machine learning, audio analysis, and multimedia. And we were, frankly, fairly successful publishing across a broad of the top venues for those areas. To get a sense of how that worked, let's look at the problem of image classification. So we're in the development of the machine learning algorithm, we might use a whole battery of different handcrafted features, which we will apply to the input image. And then most often used a trained classifier such as a support vector machine to actually classify the image. This was not just an example, this is work that we actually did, and we published that in an article, Fast Support Vector Machine Training Classification on Graphics Processors, and it was fairly successful for the problem that it was addressing. And more broadly, we worked across a number of problems in computer vision. We orchestrated quite a number of individual machine learning algorithms here. So I list those here, such as convolution, k-means, mean shift, and so forth. And we also worked on speech recognition, audio analysis, again, using problems or approaches like k-means, Gaussian mixture modules, and other machine learning methods. But in 2012, something very significant happened. What I'm showing on the y-axis here is the top 5 error rate on a standard image classification benchmark known as ImageNet. And what we see here is a very dramatic reduction in the error rate in a single year, and that was due to the use of a deep neural net called AlexNet. Now, I want to contrast then this use of a deep neural net with supervised machine learning. And really, in the general structure, they're very similar, but at the core of deep neural nets or deep learning is the use of a deep neural net rather than one or more machine learning algorithms. And I described that more in this slide, where at the top we see, again, kind of what we call a classical machine learning approach to image classification. We're given an image as input. We extract a bunch of handcrafted features, which are predefined, features such as histogram and gradients and so forth. And then we've pre-trained a classifier, such as support vector machine, to do the classification. Below, what we have is about a 9-layer hidden layer net, in which in the first part, we actually learn the features. We don't have any predefined handcrafted features. And at the end, we use a trained classifier that's, again, trained on the data. But there's a kind of a homogeneous approach used throughout this in the deep neural net. And so what we found when we began to apply that, and researchers around the world found, is that this huge battery of different machine learning algorithms that we had applied to these problems soon became replaced by deep neural nets. And so I illustrate this here across these problems of computer vision, audio analysis, multimedia, and natural language processing. Every one of those problems was not just solved in some vague sense by deep learning, But these broad sets of problems were solved by oftentimes just a single branch of a variety of neural networks. So today I'll be talking exclusively about deep learning and deep neural nets. And now I'll transition into how one actually applies these in practice. So if you want to use deep neural nets in practice, there's probably nothing simpler than just downloading the deep neural net. What I show here is kind of a hierarchy of methods of using deep learning and deep neural nets, from the most straightforward at the bottom to the most sophisticated at the top. So there are a variety of deep neural net families that are available for download. Google's been very gracious in making their MobileNet family available. I have a colleague, Song Han at MIT, who's made his family of nets available. We at Berkeley have developed the Squeeze family of deep neural nets, and over the years, we increasingly collaborate with Facebook, of which the most recent result of that collaboration has been the FBNet v3 family. There are two major repositories that come to mind of deep neural nets. That's again the model, and that's been pre-trained. So there's Model Zoo as well as Papers with Code. And then there's also a number of powerful frameworks for using these deep neural nets. I think among the most popular are PyTorch and TensorFlow, but there are a variety of others. So with those, you can go ahead and say, if you're looking for an object detector that you want to use in say, a Walmart's, you can go ahead and download, say, a YOLO object detector. If you look carefully, that pre-trained model, however, may have been trained on German auto data, both trained and tested. And so, as one might expect, it works very well on identifying cars in auto traffic in Germany. And we might expect that it also works pretty well on US driving conditions. But we may not be sure that it will meet our needs if we try to apply it to identifying objects in a supermarket. So the next step of progress that people employ when applying deep neural nets is to augment the data set and incrementally train. So we started with a pre-trained model, but we're now going to augment with additional data and incrementally train. And I like this sequence that Andre Karpathy now at Tesla put together, that back when he was a graduate student at Stanford, there in the blue, he felt that the bulk of deep neural nets and deep learning was all about developing models and algorithms, and there was a very small amount devoted to data sets, small importance to data sets. But since he's at Tesla, if you look on the right there, he sees a much larger percentage of data sets and much less in models and algorithms. And in fact, I think he's, as he's expressed on other occasions, he's been kind of overstating the power of models here and would put even more emphasis on data sets. So what I show here is a overall structure of kind of the technical, getting more in the technical details of how one applies deep neural nets. And the first here in the upper right is aggregating the training data. And as I go into the technical details here, I have to warn you, this is going to be something of a whirlwind tour where I just briefly touch on particular technical topics that give you pointers for further reading. So as I discovered at DeepScale, a startup that I co-founded with my grad student, Forstian Dola, focused on ADAS and autonomous vehicles, the quality of deep neural nets entirely depends on the data that they're trained on, and gathering data is relatively easy. So what you see here is beside one of our cars that we use for gathering data. So once you gather that data, then you have to annotate it for it to be useful. And so what I'm showing here is the tool that we developed here at Berkeley for accelerating LiDAR annotation, which is particularly problematic to use. So we use these images to assist annotating LiDAR. We have a one-click annotation approach, and then we use tracking of the objects themselves using previous annotations to predict future one. And using these, we were able to get a 6x speed up in annotation. Now, I use this just by way of illustration. Obviously, your needs, say in a Walmart, might be very different, but if you're doing a lot of data annotation, then certainly tools to improve that or speed up that annotation are really useful. Now, once you annotated your data, you want to get the most mileage out of it you can, that is the most utility. And so one of the most common, or I would say more than common, universal approaches here is what's called data augmentation. And this is simply to take for each image, say, for example, one flips, rotates, takes various croppings of it, may jitter the color, enhance the edges, or do other permutative approaches. And an approach that we have exploited in our own research is what we would call a step beyond that, which is domain randomization, in which one essentially takes various levels of the feature pyramid of an image and permutes it with various auxiliary domains. So what you see here in A through G are resulting images where we take original source image and we do something more than just randomly change the color. We actually permute it with entirely different domains, getting scenes that in some sense seem very unrealistic, but our experience is that actually improves the classification quality. Even after these, however, if we go back to the original problem that we're trying to solve, if we apply these approaches of augmentation, randomization, and so forth, can we then hope that our object detector that was developed for autonomous driving will work in a supermarket? Probably not. Probably we need even more sophisticated approaches. So one of this family of approaches is called domain adaptation. And what I'm showing here is the way in which a variety of different domains can be kind of mashed up together to allow you to more easily adapt to new domains, which you haven't seen yet. And what I'm showing, this is a very, very active area of research in which we frankly, in my group, play a role, but a minor role, given the magnitude of efforts. So what I'm showing you are recent, in particular, recent publications, the latest CVPR conference, but some of our prior efforts of using domain adaptation, as I mentioned, different augmentation policies for self-supervised learning, and then also efforts in unsupervised learning. These are all techniques that can be applied to get more generalization power. These approaches, I would say in general, have the characteristic that you, particularly the semi-supervised and unsupervised approaches, they require more data and more training, but less time-consuming labels. Now, I do have to say that as I look over these approaches, it's a significant portion of the computer vision research area is currently working on the problem of how to generalize to new domains. There's a lot of mathematical formulas and so forth. There's a lot of different approaches being tried. But at the end of the day, it's very hard to determine if one applies these techniques, how much you will be able to adapt to a new domain, such as from a roadway to a supermarket. And I think we cannot understate the power of pragmatics here. So another tweet from Andrei Karpathy says he actually sees more significant improvements from training data distribution search, that is looking at the data splits as you train and oversampling ratios, the neural architecture search. The latter is so overrated. So what he's emphasizing here is the tremendous power of different techniques, really pragmatic approaches that one uses during training the deep neural net, and the importance of curating the data as you do that. So with that, we have talked about ways to augment the data set, and now let's discuss the actual training process, because we need to incrementally train with that data. In the upper left-hand corner of the slide, I put training in context, and we're now going to talk about rapid training and techniques to accelerate training. Although we're simply doing incremental training, those techniques might not be necessary, but this is a convenient time to talk about training as a whole, because we'll be needing to get into that later. So when we talk about training, we are talking about a data set, and we've already talked in general about aggregating data set. When we talk about progress in training, a very standard benchmark for discussing progress in training of deep neural nets for computer vision has been the ImageNet dataset, because it contains 1.2 million labeled training data. And just over the last 6 years, there's been a lot of progress, and it was just back in 2015 that even Google's Jeff Dean complained about the slowness of training deep neural nets. Now, over these last 6 years, essentially it's been one approach which has dramatically improved our ability and reduced the time required to train a deep neural net, and that is distributed training. The algorithm used is synchronous stochastic gradient descent. And in this, at each step of the algorithm, one takes simply a batch or a piece of the overall data, say 1,000 images out of the 1.2 million training set, and computes the gradient updates for all the weights in the deep neural net relative to that batch. Now we see in play here kind of two competing forces. True to the algorithm, to remain true to the algorithm and what we know about the algorithm, we need to take a relatively smaller batch size in order to retain the accuracy. If we took the entire data set at a time, for example, use the full 1.2 million images in a single iteration, then we know that accuracy would go down. On the other hand, if we're going to use distributed training, we have to keep all those processors busy. So that wants us to take a bigger batch so that we can have plenty of work for all the processors to do. So what we show in this particular example is kind of a compromise, where out of those 1.2 million images, we take a batch of size 1,000 and break that into mini batches of size 64 and distribute those across 16 processors. Now, I don't have time to go into the details of the progress here, but I am proud to say that I think this is one area where our research group has had some particular impact. So I show training time in the y-axis and the number of processing element nodes which are used in the training along the x-axis. And I believe we were the first to really show significant progress towards distributing the training of deep neural nets on the ImageNet. And we reduced that time to 10.5 hours back in 2016. And then with that, then a number of commercial groups that had been working internally on training probably in fact had superior results did come forward with improved results in rapid succession. And we regained the lead, so to speak, briefly when we bulked up the number of nodes we were able to employ on ImageNet to 2,000 using a technique called LARS, developed by a student I collaborated with, Yang Yu. And then after that, ever since then, it's been commercial groups which have typically had the best results on training ImageNet, training, say, ResNet 50 on ImageNet. But we did have another impact with the LAM algorithm, which was used in collaboration with Google to reduce the training time of the natural language understanding neural net BERT to only 76 minutes. So that's just very lightly on the progress in that area. I do want to leave you with a kind of caveat regarding progress in deep neural net training. And that is that the stochastic gradient descent algorithm is very sensitive to hyperparameters like initialization, the warm-up period, precise learning rate used, the momentum, the batch size, and the original network architecture. And if you don't get those hyperparameters correct, then you can still see a degradation in accuracy, poor generalizability, even a vulnerability to adversarial attack, and of course, longer training time if you don't get them correct. So far, what we've talked about in downloading deep neural net and augmenting the data set and incremental training is a focus on accuracy. And next, I'd like to talk about improving the efficiency, which really gets down to the business of designing and training the deep neural net itself. And as you can see, finding the right deep neural network is very much at the center of our efforts. So what we learned from our experience with SqueezeNet is that there are really two important aspects of deep neural net design. And with SqueezeNet, relative to that breakthrough net AlexNet, we were able to reduce the model size, as you see on the far right, by a factor of 50x, simply through model design, simply through the way in which we structured the various layers of the deep neural network. And then we were further able to reduce the size of that deep neural net model by another factor of 10 through what's various called model compression or optimization. So I'll be talking about both of these aspects. And our general philosophy there was not the prevailing notion that bigger is better. Bigger was naturally achieving greater and greater accuracy on the computer vision image classification benchmarks. But we were interested in going to a counter trend, kind of inspired by E.F. Schumacher, that small is beautiful, which is finding just the right sized efforts for the particular applications that we were pursuing. So smaller neural nets have a significant advantage. Oftentimes they train faster, although there are some details to be worked out there. They can result, or most often result, in faster inference. They use less energy, and in that they use less memory footprint. They also enable over-the-air updates. So we applied that approach over the ensuing years and up to the present to a variety of problems. First, image classification, and then with squeeze-net object detection, and then with squeeze-seg versions 1 and 2, and now 3, various problems in semantic segmentation. And more recently, we worked at other problems outside of computer vision and speech recognition, natural language understanding, and text-to-speech. And I won't go into those further now because I'll be talking more about those later. In that process, we got kind of a feeling for the palette of the artistic palette of a deep neural net architect with different convolution types, spatial convolutions, pointwise convolutions, stepwise convolutions, approaches of channel shuffling, and we even invented our own layer type of shift. And I got then invited in subsequent venues to give talks on efficient deep neural net design. But we should observe that this manual design is both consuming of human time as well as computational time, significant computational resources. Now, granted, we were just getting started when we developed SqueezeNet, but I think Forcindola estimates that he looked at over 1,000 different neural net architectures, and that all together there was something like 384,000 GPU hours were expended. So the natural question here is, can we automate this process? And indeed we can. And I see that as something of a step higher in the hierarchy of sophistication in using deep neural nets and deep learning, which is to apply neural architecture search. So this in a single slide overviews collaborative work that we did with Facebook in neural architecture search. And I'll go through the different elements of this quickly. So first, in any kind of search, there's the definition of the search space over which you will search. And in this case, it's encapsulated in what was called a stochastic supernet. And what we see on the left hand are broad characteristics of a particular supernet. This is done for mobile image classification. So you predefine 22 layers with 7 groups. You have base channel sizes of each group are predetermined, and the downsampling schedule is defined at first, third, fourth, fifth, and sixth. And each layer can choose a variation of the template module, which is shown on the right here. And so essentially you have particular choices there with respect to the elements of the different convolutional elements, and also the kernel size and the expansion ratio. To determine the latency of a particular point in design space. So again, in design space exploration, the evaluation of the quality of a particular point in the space is very important. And we want to move from max and model parameters to actual latency values on the actual target. And so we were essentially characterized each individual layer on the target to get those values for the latency. And then we just plugged in the results into the loss function and optimized as before. Now, this differential neural architecture search, or casting neural architecture search into a differential format, which made it amenable to optimization, was relative to prior approaches extremely fast. And so using only 8 GPUs in 24 hours, we were able to get a result. We were also able to optimize for the actual latency, as opposed to just optimizing max or memory size, number of model parameters. And it could also be generalized and applied to different problems. And again, I want to reemphasize that this was done in collaboration, close collaboration with Facebook. This work is not continued with my students, but with a student with another advisor, Joey Gonzalez at Berkeley. Alvin Wan has continued to develop 2 more generations of the FBNet family with version 2, in which the channel dimensions were thrown into the optimization, and version 3, in which pre-training was used to improve the search efficiency. And I'm not going to throw a lot of results tables at you, but this one is interesting because I do think it reflects the state of the art, achieving this very high level of accuracy on the Y dimension with fewer flops than other approaches for mobile nets. But I do want to leave you with the sense that the challenge in the adoption of neural architecture search is that it requires just as much expertise as the original deep neural net design here. So let me just move this down to show you on the right hand, where again, this is one more case where there are many parameters to be explored here, and they can be as daunting as doing the original deep neural net design itself. So with that, that's as much as I'll say today about the actual process of designing the deep neural net, but I did want to get back to this issue of optimizing the deep neural net. And going back to this diagram, we see it here at the bottom, generally under the heading of efficiently implementing the DNN. So I'd like to start by talking about quantization. So uniform quantization is just a mapping from floating point values to quantized integer values. So at the top here on the left, we see floating point values, which can take 16 or 32 or bits or even more, down to 8 bits. And then on the right-hand side, we see, say, floating point 32 values with their corresponding int 8 values. And the advantage here is obvious. You're reducing the number of bits required to store the same, say, weight or activation. Now, there are many things that come from this. What I show on the right here is a off-quoted graph which describes the relative energy cost of various arithmetic operations, beginning with an 8-bit add, all the way up to a 32-bit DRAM read. And you can see that's a factor of 640. Relatively speaking. So lower precision also means higher throughput, and so these are a little bit idealized values. I should also mention that although I've often talked about embedded applications, here the results that I'm showing are relative to NVIDIA Turing GPUs with their Int4 tensor cores. And so with the obvious memory reduction on the far right, we actually see also a higher throughput for mathematical operations going up to, say, a factor of 32 within 4. Lower precision means lower latency, and so the speedups are shown here for batch 1 and batch 8, comparing floating point 32 again to int 8, and you can see factors of 4 to 7 there in terms of the actual speedup. Lower precision multiply accumulates reduce the energy, and so what I have here are data from Marian Verhulst, in which she gives on the left here the various bits in an integer MAC and the corresponding tops per watt improvements here is as much as, say, a factor of 10 to 20. And this is presuming that you can appropriately size the MAC units for the new bit precision value. And this is essentially another way of looking at the same data, but this is from a later paper, 28 nanometer process with the tops per watt improving from 5 to 10 here. So just how do you do that? How do you implement this mixed precision quantization? So what I show here is, and the approach that we've taken is a layer by layer approach, and that's going to be very important. And what we can see here is given the number of layers in a network and given the number of bit precision choices, we have very much an exponential search space to consider for each layer, weights and activations, what bit precision should we use? So I'm just going to touch briefly on the general approach that we take. And the key insight here is to what if we better understood the loss landscape associated with the function that we're using to optimize the deep neural net. And the way that figures in here is as we go layer by layer, we make a simple observation, which is that if the loss landscape is relatively flat, then that means it'll be less sensitive to reductions in bit precision, and therefore we can quantize more aggressively. So that would be an example on the far right there. But if we look above, the more folded loss landscape on the far left, we will need more bits of precision in order to avoid losing accuracy. So I guess I should emphasize here, of course, it's relatively straightforward to quantize and just change the bit precision of a deep neural net implementation. The challenge is to retain the accuracy of the original deep neural net. So we have developed the algorithms as well as the corresponding software over a series of generations of this work, and presented that in 3 generations of Hawk papers. We've also mainly been focusing here on the problems associated with computer vision implicitly, but we've applied these same techniques to the large BERT model, where we were able to, among the first, well, we're indeed the first to go below 8-bit quantization for quantizing the BERT model. And the principles were precisely the same, which is why we were able to quantize it so quickly. We need more bits for sensitive layers and fewer bits for less sensitive layers. Now, as I said, quantizing is easy, but we want to retain accuracy, and the challenge in maintaining accuracy is that we need to, during the process of quantizing, we need a fine-tuning process or a retraining process. And that's computationally time-consuming because that involves essentially putting training in the inner loop of the optimization. And also the training data, which you need to retrain the model, may in fact not be available, either due to privacy or security concerns. And this is in the case of medical data, or it's simply that data is no longer at hand for a variety of reasons. So to address this problem, what we did was we used the same basic intuition that we wanted to look at the sensitivity of particular layers to bit precision, but rather than computing the full loss landscape based on data, we simply used here in this work a refined Gaussian as the input, and used that as a measure of sensitivity. And there we were able to get a 4 to 8x reduction in model size. Now, that addressed one of the limitations of quantization. Another limitation is that even though you may result in fewer bit precision or lower bit precision for weights and activations, there may still be expensive floating point operations in the quantization process as well as in the actual inference itself. And there are a number of, particularly at the edge, a number of integer-only hardware units. That is, they don't actually support floating point at all. So for these approaches, for these processors, those approaches would be completely inappropriate. So examples of those are the Greenwaves technologies, the Cortex-M family in ARM, and even the Google Edge TPU. So to address that, we have developed a purely integer approach to quantization in which all aspects of the quantization as well as all aspects of the inference are done only in integer. And this was relatively easier to do for computer vision models. So we actually took a more challenging model, the BERT model, and we were able to do that entirely in int8, integer only quantization, getting a speed up of 3 to 4x. And then we also, as it happened, improved the accuracy in the process. We've also looked at the speech recognition, and we have a similar approach that we've applied there, resulting in a model that's 6x smaller and with a very modest 0.25 degradation in the word error rate. And we feel that we've been at this long enough that it's been satisfying to take a step back and not just try to survey our own work, which we've been working on for a number of years, but very broadly survey the work in quantization. And that will be showing up in as an invited book chapter in low power computer vision, and it's currently available in archive. So the last step of the hierarchy here is in which you actually design the deep neural net simultaneously with the neural net accelerator, or co-design it. And although this hasn't been a very much of a focal effort of ours, it has been very educational in helping us to understand how the neural nets match to hardware. So our first effort here was done in collaboration with Samsung, where integrated circuit chip architect from Samsung joined us for a year, and he was developing a computational neural net accelerator to be used as an IP block for mobile systems on a chip. And so we co-designed a net squeeze next together with the squeeze accelerator, and we saw basically the interactions among the data movement there and how they could be improved. And the results there actually showed he was able to improve accelerator performance on nets like mobile nets v1 by as much as 6x. We then went on to our own efforts here, in which we developed another neural net, again for computer vision applications, and we were able to get state-of-the-art results there and superior frame rates, much superior frame rates to those that were available. But to me, the most interesting thing is that by using our work in quantization, we were able to get bit quantization down to a level in which we were able to put 1,024 multiply accumulate units on a low-end Xilinx ZU3 device. Our work following that was more involved in less solving general problems like image classification and more very particular problems targeted for FPGA implementation. And so we worked on deformable convolutions and deformable parts models, and we were able to achieve 2x the frame rate of commercial implementation, same accuracy, by putting together the neural architecture, quantization, and developing our own hardware engine. And we've gone on then to do a whole design space exploration, particularly targeted for FPGAs, which again, we're able to get 2x frames per second with equivalent accuracy on standard problems. But more importantly, we're able to explore a very broad range of trade-offs of accuracy and efficiency. Those are just our own efforts, and as I say, in some regards, I view them as more our own education than ultimately impactful. But there's a tremendous array of commercial efforts out there exploring the same problems of how do we better tailor hardware to support neural nets, and how do we better tailor neural nets given the target hardware. And so what I show along the y-axis here are the absolute tops, and then along the x-axis the number of basically the thermal design point, or the power regime in which they operate, ranging from smartwatches through smart speakers and cameras, smartphones, up to independent edge accelerators. So I don't think we've seen the full impact of these yet, but I think when we do, it's really going to change our whole notion of what's available in computation at the edge. So last, I'd like to just wrap up, and I've done a lot of kind of discussing individual research contribution by individual research contribution and how they broadly fit together. But what I'd like here to wrap up at the end is really talk about, well, what's this going to make possible? And the particular class of problems that I'm looking at most here are the notion of conversational interfaces, because I feel like whether you're wearing something like an Oculus Rift virtual reality, or you've got some futuristic augmented reality device with a heads-up display that you're actually wearing like glasses, or whether you're just talking to your mobile phone, or perhaps you're just trying to make an order at a quick service restaurant. In all of these cases, I think what you want is, you certainly don't want a keyboard or some emulation of it. What you want to do is just be able to converse freely with the device and have it respond accordingly. So I mentioned this briefly earlier, but this has been the focus of a lot of our research over the last 2 years. And in the last 2 years, we put together a flow in which one is able to take voice input and, using deep neural nets, then perform speech recognition. So you might get an audio in and output the word sequence, "Where are the bananas?" And then that goes into a natural language understanding, particularly cued for an application in which it identifies that the intent here is to find the location of some entity, and the entity is bananas. And then in this question answering, it answers aisle 1. And then, given that aisle 1, we then have the problem of actually producing then voice output. We don't want to belabor people with having to look at some screen or something. We actually want to voice output and synthesize aisle 1. So with that, I think we can imagine taking the Walmart service kiosk a step further. So rather than just having kind of a touch or text interface to pick something up, one can imagine a kiosk in which one is able to just kind of stroll up and ask questions like, "Where are the bananas?" And then, given the question, "Where are the bananas?" This little kiosk is using entirely local processing without accessing the without accessing the cloud, is able to respond, "Bananas are on aisle 1." So that's all possible. But I do have to kind of mention certain caveats. As I've alluded along the way here, there continue to be problems on gathering, annotating data, as well as trying to use not just supervised, but unsupervised and semi-supervised learning, and generalized to new examples. Training has come a long way with massive speed ups, but still typical training will require some expertise in adjusting the hyperparameters to be successful. And similarly for neural architecture search, we've come a long way from just somewhat randomly pursuing the design space in some manual fashion through neural architecture search, but that neural architecture search itself has its own hyperparameters to be adjusted. Nevertheless, I am here to tell you that you can climb the hierarchy from downloading deep neural nets, through then learning to augment the data set and incrementally train, through designing your own deep neural net and training it, to using neural architecture search to design that deep neural net, to then optimizing the deep neural net for more efficient implementation, and even getting down into the details of the hardware and matching the neural net accelerator to the co-design of the deep neural net. And we've published broadly over these areas in just the last few years. And I do, before I finish here, want to thank the team, everything I've reported here.
Welcome to this session of Converge. Happy to chair this panel. We have 4 eminent panelists with us. Would be my pleasure to introduce them. We have with us Keutzer, professor of ECS at University of California, Berkeley, where he's a member of the BAIR lab, and he's the co-director of the Berkeley Deep Drive Research Consortium. His research covers all aspects of deep learning, including the computational complexities and many of them. Kurt is also an entrepreneur and he has been an investor and advisor to over 30 startups. We also have with us Professor Chiranjib Bhattacharya, who is chair in Department of Computer Science and Automation, Indian Institute of Science, Bangalore. His research interests are in foundations of machine learning optimization and how they apply to industrial problems. He's authored numerous papers in leading journals and conferences in ML and has won many best paper awards. And he joined the Department of CSA of ISC in 2002 as an assistant professor. And prior to that, he was a postdoctoral fellow at UC Berkeley. He holds an BE and ME degree in electrical engineering from Jadavpur University and ISC. And he's finished his PhD from the Department of CSA at ISC. He's also a fellow of the Indian Academy of Engineering. We also have with us Professor Ravindran, who heads the Robert Bosch Center for Data Science and Artificial Intelligence at IITM, the leading interdisciplinary AI research center in India. He is the Mindtree Faculty Fellow and Professor in the Computer Science and Engineering Department at IITM. Currently, his research interests are centered on learning from and through interactions and span the areas of geometric deep learning as well as reinforcement learning. He receives his PhD from the UMass Amherst and his master's degree from the ISC Bangalore. We also have an industrial person on the panel, which is Chintan Shah. He's a product leader at NVIDIA, focusing on AI products for intelligent video analytics and conversational AI. He manages AI software and tools for building and deployment of AI models and applications. He's fascinated in seeing how AI has accelerated so many traditional industries and all the innovations that it has driven. In his previous role, he was developing cutting-edge NVIDIA GPUs. He holds a master's degree in electrical engineering from NC State University. So glad to be on this panel. And this is Vijay Agneeswaran, Director of Data Sciences at Walmart Global Tech. So glad to be on this panel. We are going to talk about some of the challenges in industrialization of machine learning and deep learning. So without ado, right, I'll get on to the questions and start asking the panelists. So the first question I had was on mainly the challenges in industrialization of ML models. So specifically, right, what are the challenges some of you have faced in putting ML models into production? One of the things that at least we have faced in Walmart, right, is as we have seen, right, the actual ML model development, right, is only a small part of the overall engineering that is required, right, to get ML models right into production. It's only about 20% is actually the model building, but remaining 80% is the engineering necessary to put models into production. Starting from ingestion of data from multiple sources to being able to transform the data in various forms into forms which machine learning can actually leverage, plus training models at scale, taking care of all of the infrastructure issues, as well as being able to productionize the models, right? That includes model serving and taking care of the entire ML life cycle itself, right? So these are some of the things that we have faced, but the right, which I would really ask is what has been the experience of the panelists themselves, and what are those issues they have faced? Is it the ML engineering, or is it data availability in terms of labeled data, some of that? So maybe we'll start with Kurt and then go over to the others. So Kurt, over to you.
So first, let's do a little tune up on the terminology. So I notice that people often say AI, people often say ML and so forth, and yet they say that at the beginning of their talk and then immediately they show a deep neural net, right? So what I'm going to be talking about is basically deep neural net centric, or sometimes it's called deep learning. And you can all decide whether that's AI or ML, but I'm going to be specific about what I'm talking about. And Vijay, I think you contextualized the problem very well, but I'm going to briefly go kind of bottom up from the model itself. With the models themselves, the two challenges we faced are basically robustness or generalizability and efficiency, because if the model's not efficient enough, then you can't use it at all. So there's really no point. And even if you can use it, if it's efficient enough to use, you can afford the computation to use it. Then the question is, does it adapt to the ever-changing data which you have? So those are kind of at the model level two of the issues. I think you're absolutely right that the model development per se is dwarfed by the issues associated with data. Data collection, data annotation, and so forth. And there are various research in self-supervised, unsupervised learning, and so forth, as well as domain adaptation, domain randomization, and so forth, to try to address those. And then even more broadly, as you say, there's the whole issue of what is the life cycle of this? How is this actually deployed, and so forth? So there's layers and layers of issues. So I think in some sense, particularly for us as academics or as industrial researchers, the question is just where do we value add? And I think that in some sense we're right to kind of focus in this hierarchy, first with the model, then with the data, then maybe some MLOps issues and so forth, and then leave a lot of the engineering issues of life cycle and so forth to those of you who have the particular context.
Yeah, that's a great answer, Kurt. Yeah, I understand. I mean, would you want to elaborate a little more on both of these issues, the efficiency and the other one you talked about? Maybe you could talk about it a little bit deeper and
Sure.
maybe for a couple of minutes.
I don't want to hog the panel, but
Yeah.
I mean, efficiency, it's just, we read about or blog posts every day about, or at least every week or two about some new model that's getting amazingly level superhuman efficiency, or superhuman results and so forth in terms of accuracy. But it could be years away from actually being able to use that model in a computationally efficient manner. Some of these models like GPT-3 require $1 million simply to train, right? That's not something you're going to be doing for an average application and so forth. So our first challenge is to make them efficient enough, both in the training and the inference, the actual deployment of the model, so that they can actually we can afford to use them. And that requires a large battery of computational techniques, which I think we'll be talking about later in terms of the education that's required. And then the other issue is certainly we learn this very well in autonomous driving, is that you work very hard on these models. You think you've gathered a lot of data and so forth, and then the weather changes. It's deployed, say, in an area with more rain or foggier, and the models just don't hold up. So there's this issue of model robustness or model generalizability. And again, there's a huge battery. It's not like we're flat-footed about this. I think in both industrial and academic research, there's a large body of research, which I won't try to briefly review here, that's being applied to try to address those issues.
Thanks, Kurt. That was pretty awesome. So Chintan, what's your take on this? Because I know you've been productionizing models for quite a while. So if you could give us your perspective, that would be great.
Yeah, thank you, Vijay. And I agree with what Kurt said about efficiency of the model and accuracy. And in fact, they kind of sit at the opposite spectrum. You want to make the model to productize, you need both. You want to be able to detect good accuracy, but at the same time, when you productize it, you need that performance, because at the end of the day, when you productize, you want to reduce the cost. This is the cost of training the model. This is the cost of deploying the model. So it's very essential to kind of look at both spectrum. So I'm not going to go too much into what Kurt mentioned. Some of the challenges that we have seen in terms of improving the accuracy is we want to generalize a model. We don't want a model to just work on one thing. So when you generalize, you have to make sure that you get the right data. Getting the data is very expensive. Annotating the data is very expensive, and it's just not expensive. It's also very time consuming. So you have to factor in the time it takes to collect and annotate the data. And then when you generalize the model, you have to make sure you look out for corner cases. If you're doing like a vision-based model, different lighting condition that this particular model gets deployed in, any weird camera angles that you have to account for. And last but not least is when you're creating those models for a lot of for things like people analytics or anything to do with humans or even car, anywhere there is a biometric information, you have to look out for the privacy concern that you cannot just collect data anywhere and use it to train a model. So that's another thing that we run across is we have to make sure that the model that we get is clean, we have the permission to build a model from that data set. So those are some of the challenges that we normally run across when we are productizing a model.
Great, Chintan. Yeah. Thanks for that. That's pretty useful industrial perspective on this. Just had one more question before we move on, right? Pretty related to this, right? Because Kurt was talking about robustness, right? It kind of struck me that robustness and accuracy themselves may be slightly orthogonal concepts, right? Any thoughts on that from Chiru or Ravi before we move on?
So, in fact, I had a thing that I wanted to add on to what Chintan said towards the end. Then I'll come back to your question.
Oh, okay, go ahead.
So this is something which academics, right? We never had to worry about. I mean, the provenance of the data. You know? So
Right.
in fact, so in our center, right? So we have some people on our advisory board who are very pushed us towards, getting an ethical officer on board. And I don't think any AI center, at least in India, doesn't have an ethics officer right now associated with it. And so we have to look at things in a very, very different light. That we're using a traffic video data set that we generated in Indian context for about a year until this ethics officer took a look at it and said, hey, in some of the cars, the number plates are visible. And I know you're not tracking number plates in your application, but you shouldn't have published this data.
Right.
And that was like new to us, I mean, hey, look, they're identifying different cars and telling you whether it's a Maruti 800 or it's a truck or a moped, and that's what we were all worried about. We never thought about the number plate thing. So we have to now basically, pull the data and make sure that it's sufficiently anonymized. Other option is to go find the owners of the vehicle and get their permission. That's never going to happen. Right? So these are so many different things, even before we go to productionizing, right? Whenever we start interacting with real data, there's so many issues that come up in AI that we as researchers, but happily working on UCI data, right? We never worried about before. So I think many issues are opening up. So coming back to your question, robustness and accuracy, sure, you could potentially think of them as being orthogonal, but it depends all on your definition of what you really mean by robust here, right? So. And if it is things that are robust to perturbations in the input, right, adversarial attacks and so on and so forth, I don't necessarily think that has is an enemy of accuracy. In fact, sometimes making your model robust to adversarial attacks actually can improve the performance of your model. This is not always the case, especially with deep learning models. It's not always the case that robustness and accuracy are at loggerheads, but in general, maybe.
Yeah, great, Ravi. Thanks. So, Chiru, any thoughts on this before we move on to the next question? Because I know this robustness, accuracy, these are quite interesting topics. So, if you have any thoughts on it, we would love to hear. Yeah.
So, maybe what I said was 2 points. So, one is that there is this debate about robustness versus accuracy. So in the past research in pre-deep learning world where we could show explicit trade-off between the so-called margin which determines generalization error with robustness. If you want more robustness, you have to sacrifice margin and hence generalization, and hence that will show up as accuracy levels, right? The other point is important is when you talk about robustness, often also in today's world, you also want to mean that the models could be easily deployable from lab to the field outside. Now, often the parameter settings or accuracy measures, etc., may not be suitable. That's what we are now finding for direct deployment in the field. So while the story about what is the trade-off you get to build a more robust model, which is more field deployable, that story is, the jury is still out, but at top conferences, I think people are thinking about how to define new loss functions, etc., to address that. Yeah, so that's all I had to say, add to the point, Vijay.
Yeah, great. Yeah, thanks for that, Chiru.
Vijay, if I could just add one thing. When I said robustness,
Yeah.
basically, I meant precisely accuracy, but in diverse environments. So maybe more like generalizability. Of course, robustness can also mean robust in the face of, say, pixel level perturbation, or robust with regard to adversarial attack. That wasn't how I was using the term.
Oh, okay, got it. Yeah, okay. All right. So the second question I had was, what are the specific research topics, within deep learning that some of you are pursuing, which would help, for example, facing those challenges that we have been talking about, right? Maybe it could be few shot learning, or addressing the computation complexity of deep learning. It could be semi-supervised learning, or even unsupervised. So those are all could be, but then I would love to have your points of view on this. So maybe we'll start with Ravi on this.
So one of the things that I have been looking at more recently is trying to move towards using more symbolic representations while you are also trying to use deep learning in some way, right? So the goal here is to make sure that it is easier for a human in the loop to interact with AI systems. So in that some sense that helps with the deployability. So right now it's more in the research side, right? So we're not really looking at field deployability yet. There are things like where a human is able to write simple rules in terms of these symbolic representation, and that can then be used to generate label data for a deep learner, which can then provide more fine-grained generalization than what the rules say. So it's like learning with weak supervision with symbolic representation filling in the gap. So that is one direction that we are looking at. And then there's a lot of work on explainability in our center. And one thing that we have been working closely with some radiologists is to build models that analyze radiology images, but are also more explainable or more interpretable for an expert in the domain, right? So can they actually attach semantic signals to some of the features that are being generated? So that's some work done by my colleagues. And we also in the space of trying to use first principle models, right? So especially because we do a lot of work in the manufacturing setting, and quite often in that domain, you find people are very wedded to their first principle models. Right? They have like 15 different coupled partial differential equations which explain how their system evolves, and they are loath to throw it out and then adopt a black box model. So what we are looking on is, hey, how can I actually take that first principle model and then figure out what is the gap that can be bridged by using data-driven methods, whether it is simple classifiers or predictors, or whether it is some kind of a more complex deep learning system. And we've had quite a good success rate. In fact, we worked with the company in improving the digital twin models. We took their simulators, but then added a layer on top of it, a deep layer on top of it that made it work much better. These are some of the topics that we're working at. I mean, if time permits, I can add more down the line.
Sure, Ravi. Thanks for that. So Chiru, maybe your thoughts also would be welcome here.
Our group personally is looking into 3 specific issues which we think have ramifications in the industrial world, both in the short term and the long term. So in the short term, we are pursuing things on what is known as model compression, and especially with a focus on edge computing. For example, we now have results to show that we can make a drone autonomously fly with a very low-end processor like our Android board. So this requires completely rethinking of how machine learning needs to be redesigned. So this is one line of thread which we call model compression. The second part, which in the medium term will have a lot of impact, is something which Ravi also is trying to pursue in his group, is about radiology and X-ray images. So I am not sure how many of you know this. If you can look up xraysetu.com, that's a project which I am I'm part of it and maybe leading it, if you can say that, with others at ISE. So there we are looking at X-ray images and try to give semantic annotation and predict COVID and things like that. This is more like emergency response, but I think that will go, that thread will continue. And thirdly, in the long run, we believe that the deep learning, the success we are seeing, is essentially depends on quality of labels. Now, we soon, the way the world is exploding with data, if you really want to get to the next level, we have to come up with algorithms which do not rely so much on the labels and are capable of learning from data without labeled on, is able to learn from unlabeled data as well. So for that, we have made some progress on new models on unsupervised learning. Unfortunately, it's coming out, these papers have come out in solid computer science theory conferences like SODA and etc. In recent ICML also a couple of papers on follow-up on that. So that can be one very nice direction to build models which are unsupervised in nature. So these are the 3 points, I would like to add.
Yeah. Thanks for that, Chiru. I know Kurt has also done a lot of work in this space. Maybe a couple of lines from him before we move on.
Well, I think as this panel's aired, you'll have just heard maybe 40 minutes of me talking about this, but basically, using this tremendous herd of very bright Berkeley students, we've been able to work entirely broadly across data aggregation, accelerating training, original model design, model compression has been mentioned, and also even hardware software co-design of neural net accelerators. So we're pretty much trying, I don't know how successfully, but we're trying to cover the whole gamut of problems.
Right. Yeah, got it. All right. Okay. So we have talked about a couple of interesting questions. I had one more, which was slightly different, but yeah, it's more about the people coming into the ML and DL world, right? So essentially, right, what are the key skills required to apply machine learning and deep learning to the industry? Are students learning them in the university or not, right? That's really the question, right? So maybe we'll start with Kurt and go over the panelists. Over to you, Kurt. Yeah.
Sure. I think that obviously as educators, what we should be teaching our students is such a critical question, particularly as the techniques are changing. I mean, increasingly what used to be a process of algorithmic and development and then implementation in an imperative language like C++ or C or something has been replaced simply by the development of a deep neural net. And I think we're coping with that, but I think if our educational process is kind of organized around the old school of algorithms and imperative programming, then probably we're not doing our students a service if they want to enter this area. But I think it's also important to kind of keep with the fundamentals and kind of organizing this a little bit around this framework of we're trying to improve accuracy or robustness or generalizability. Then our students need a foundation in statistics. I think that's really critical. I wish I'd studied a bit more of that. Basic, computational linear algebra and so forth. I think that's at the core of everything we're doing. Optimization theory is up everywhere, particularly in the training of these deep neural nets, and to really understand what's going on. So many people, if their deep neural net say doesn't train, they just throw up their arms and begin to fiddle with hyperparameters without really having any sense of what's going on. Then the other broad challenge I think that we're addressing is efficiency. And efficiency, I think our high performance computing students, ironically, have done very, very well in deep learning. I'm very proud of my student, Brian Catanzaro, now a vice president at NVIDIA. He came very much from a high performance computing background. My student, Forrest Ciandola, with whom I co-founded DeepScale, he also came from high performance computing. Now, that helps you with training, but more fundamentally, it helps you really looking at the deep neural net computation as a computation and bringing that same skill set of efficient computation and so forth. There's a software stack involved, compilers and so forth. One needs to understand something about hardware architecture if one wants to make things efficient. And it's really useful to be really able to go down actually to the physical hardware, particularly if you're working with neural net accelerators and trying to decide exactly if we move from 8-bit precision to 4-bit, how much does that save? The third very broad category I would say is really sociological. And with this, having a predominantly Indian audience, I'm going to challenge you a bit. I think that my Chinese students, for example, seem to be plugged into a much bigger network. There's not a paper announced on arXiv that's not being chatted about in some WeChat group somewhere, and they're coming in the next day, pointing to something in Chinese and saying that their friend at Tsinghua has just mentioned. I don't have my Indian students coming in pointing to WhatsApp and saying, this was just on some group that I belong to. So really, the field is moving so quickly. Really understanding the models is what's new at Hugging Face, what's new on Archive, and so forth. I mean, I've really, if I called it anything other than a kind of social networking, I think I would be over academicing it somehow. I mean, I think it really is, and so I think that's as integral an element of success in these students as anything else.
Yeah, thanks for that, Kurt. That's a great answer. But over to Ravi for his thoughts. Ravi.
So, I mean, I agree with a lot of what Kurt said, right? So, in terms of what is really important to computer science, for example, a typical computer science curriculum would only probably be covering discrete math and maybe a little bit of probability theory in the past, right? But now we have to go much beyond that, and we have to do a little bit more continuous math, talk about linear algebra and at least the computational linear algebra side of things, and also expose people more to optimization so that they have some sense of what is going on. But the other thing which I'm also noticing that in the industry, right, there are a lot of different kinds of positions, right, or job descriptions that are opening up for people with some kind of AI skills, right? I mean, this range from people who know how to operate AI tools, right, to people who can actually want to work on it and build new algorithms and to have a much deeper understanding of it, right? So somewhere like I jokingly sometimes say going all the way from electrician to electrical engineer. So we have the whole gamut of job descriptions that are opening up, and I don't think the academia is still caught on to what are the different kinds of things. I mean, we can very easily train a Java developer now, but we are not. That doesn't mean that he needs to understand lambda calculus. So I mean, so that sense, right? So we really haven't hit the right kind of abstractions for what computer science curriculum should cover. But then there are a few things like Kurt was saying, the fundamentals of math. Of course, everybody has to look at it, and then as we go along, right? So we probably need to evolve into what AI curriculum should look like. So that's something which
Yeah, that's very interesting, because I think your answer goes into the, for example, in a cooking kind of a scenario, right? Do you hire actually people who have done enough cooking, or do you start looking at electrical engineers who can create the microwaves and and so on, right? Right from this level all the way to the top, who can simply use the appliances and start cooking, right? So I think that's similar to the debate that we're having. But yeah, over to Chiru for your thoughts on this.
So I think the question we were discussing are we producing the right kind of students who are fit to take on or lead the ML industry? My perspective is narrow in the sense that we only see students from our institutes. And I hear from my colleagues out in industry that given the demand our number of students we're supplying is A, too less, and B, there is some amount of skill gap, but we haven't put a finger on it that what exactly in the skill gap. So one of the things is, let us say we train a deep network model. The students, when they do those exercises on Agneeswaran's data set and thing like that, so that is a very far cry from training an industrial scale model on industrial scale data. Now, that is a challenge I think we have to address to get them job ready or industry ready, if you will. And often even the theories, the codes, etc., needs to be completely rewritten. So possibly, so maybe what we should be doing, I mean, maybe this is beyond the brief of this this panel, but probably a more rigorous internship or more embedded learning environment where you live with the data, like industrial scale data, can be a way forward to address at least that small skill gap. And I agree with the previous speakers, both Kurt and Ravi, about the curriculum. I have nothing more to add except to support their points.
Yeah, great. Chiru, thanks for that. Chintan, we would like your perspective on this too.
Thank you, everyone. You know what? I agree with everyone. I think fundamental is something that's absolutely needed. But I'm going to talk about two things which I feel is important for students coming into the AI or ML deep learning. I think first, I think this is something that Chiru mentioned about model compression. So it's along the same line. I think model efficiency is very important. And I feel that that is something that student needs to understand. How do you productize this model? How can I make it run fast so that when this model goes out in the industry, goes out in the field, I can minimize my cost, minimize the cost of the platform, of the hardware. And there are things that students can learn about, like quantization. How can I run it in lower precision, model compression, pruning, etc. Optimizing for the hardware platform is something that's good for practitioners of AI to kind of learn to kind of productize the model. The second one I feel is like actually not just creating the model, only the model, but the entire journey, the MLOps journey, starting from the data set. Like how do I collect the data set? Where do I collect the data set? Is this even a data set that is that I can use? And this comes up a lot when we are trying to commercialize a model. And most of the data set, most of the public data set, we just cannot use because it's only for research purposes. So making sure that you have the right data set. Once you have the data set, experimentation, and to kind of get the create a model that gives you the accuracy, the robustness that you need, as well as the efficiency. And then once you create this model, it's manageability of the model once it goes out in the field. How is it performing over time? So just being aware of all of those is extremely important, and not just say, okay, you collect some data set, you create a model, and then you deploy it. So just and it's the entire journey, that it's not once you ship a model, you're done. You actually have to manage the model. You have to keep improving the model, get feedback from the field, and kind of use that to kind of improve your model. So those are some of the things that I feel that students should be equipped with when they enter the field.
Yeah. Thanks, Chintan. That is pretty awesome. So probably, right, we can, in the interest of time, we'll move on, and we just have one last question, which
no, Vijay, this is a panel discussion. I have to counter something somebody else said on the panel. Otherwise, it's just a bunch of people giving their opinion. So I'm going to go. I mean, I slightly disagree with what Chintan said, right? So I think the ML ops process is becoming complex enough, right? I don't think we should be looking to produce end-to-end expertise in students that are coming out. Right. So if you're talking about people, I mean, if you want people who are good at, making sure the hardware, you match the hardware to the platform, I think you need a set of people with a very diverse background, right? People who need to actually understand, chip design to some extent, and at least go down to the level of the instruction architecture, and then they will be able to do the mapping from the hardware to or rather from the algorithm to the hardware. And at the other end, you have people who have to worry about data, and then those people have to worry about even policy issues, legal issues, ethical issues. That's a different kind of training that you would need, right? So this is exactly what I was saying. There's so many different niches that are getting opened up. You can't really talk about somebody.
Yeah, I don't disagree with you. I don't think the student needs to be an expert in all the area, but they just need to be aware of and know that, okay, these are the things that you need to actually create a model, to productize a model.
Let me pose in some sense the same issue as a question, which is when I used to teach software engineering, imperative programming, I would go to the people who were hiring my students and basically ask them, where should we stop? There's always the current debugger, there's always the current project management tool and so forth. Where do we stop? So I would pose you a similar question, which is, I mean, and I want you to ask seriously, if something like, should we be teaching our students TensorRT? Or if they know TVM or other optimization or targeting frameworks for other processors and so forth, if they worked on Qualcomm, is that enough? And I ask it and answer honestly, because if the student who knows TensorRT has an advantage in NVIDIA, well, then we should think about teaching it. So what do you think?
Well, my NVIDIA answer would be that of course you should teach at TensorRT, but no, I don't think you need to be super specific in terms of the hardware that you teach. You obviously have to teach the most common hardware, which is just like NVIDIA GPU. So I think TensorRT would be important. But I don't think you need to, at least from academia, I don't think you need to cater to just one company or one set of specific tools versus other.
Yeah, absolutely. I think this is a great debate. The fundamental thing, right, that even we have been thinking about, right, is the point that Chintan and Ravi were debating, right, whether we should teach, for example, just the foundations, or go into very specifics of ML ops and so on, right? I think that question will always be there, and we feel there are potentially gap areas there which could be addressed, right? Maybe even from a curriculum perspective, right? Though we do agree that definitely the foundations are very important, and people with good fundas can actually pick up any specific tools that are there, and they should not have trouble in picking those up. And but only thing is, yeah, from especially like we discussed, right, the one thing that seems to be happening is model building is only about 20% of the effort, but since a lot of effort goes into the other aspects of the engineering aspects of ML, right? So that's where we are seeing there could be potentially gaps in the academia, right? Especially students coming in do not seem to have those
So
aspects.
Vijay, that's exactly what Kurt's question was. Does the industry have a clear understanding of where we should leave off in academia? And I have been talking to people. In fact, I even tried engaging people in NASCOM, right, which is the IT company association here, and they don't have a clue. At least the Indian industry, they're not able to give a correct answer to it. I'm pretty sure. I mean, there are a few companies like NVIDIA or even Google that would be able to give that, but at large, right? I don't think there is a correct understanding of where should academia stop and what should be the industry-specific training. So right now, almost all training is happening at the industry in terms of using these tools. Literally zero ML ops training happens in academia, at least in India.
Yeah. No, I understand. The point I was making, right, is more fundamental, Ravi, because what I was saying is, while on one hand, the question was more on which tools should you go about teaching and all that, right? But which I was not addressing, right? What I was saying is more foundational engineering aspects is what needs to be taught, right? Around machine learning. So it's not necessarily only the foundations of model building, but also foundation of engineering, right? Need not necessarily go to the tools, but just the foundational engineering aspects would be very helpful. How do you manage the life cycle? Things like that in general, right? Yeah, Kurt, sorry, go ahead.
Well, yeah, I mean, again, I think what helps us is to look back on software engineering, right? But so there were a lot of people who said, what we really need to teach are principles of programming. And we're going to teach scheme and all this, Java is going to blow over, C++ is probably going to blow over. We teach fundamental principles. And then those people go for a programming interview and they don't do well, right? So I think we have to acknowledge that our students need to learn TensorFlow and PyTorch. They need to know how to train a model. They should probably know TensorRT or some other target framework. They should be able to dig in and probably do a little CUDA coding if they have to. And it sounds great. We'll just teach them fundamental, but they're not going to do well in a job interview if we stop there.
Absolutely, yeah. Great points made. I think this was a phenomenal debate, and happy to have been on this and enjoyed it as much as any of the others, I guess. So thanks for all the panelists. It's been a great session. Thanks, folks. We had a phenomenal session. Thanks very much.
Thank you.